I'm Norman Wildberger, and today we're going to carry on with trigonometry over a finite field. We're going to illustrate things with F7. The main thing that you need to know is that F7 is a lot like the rational numbers with one major difference. In F7, 7 equals 0. That's basically the only rule. So it means that we're still considering things of the form a over b, where a and b are integers, but now b is not divisible by 7. And two fractions are equal when AD minus BC is not equal to 0, but when 7 divides it, when it's a multiple of 7. Here's an example of a bit of arithmetic in this field. Suppose we had 5 over 9 minus 11 over 12. This 9 can be replaced by 2 because we're allowed to throw away 7. The 11 and the 12 can be replaced by 4 and 5, just subtracting 7s. This thing is computed just as in ordinary arithmetic. 5 times 5 minus 2 times 4, that's 17 over 10. Throw away some 7s, we get 3 over 3, which is equal to 1. That's a computation in F7. What makes this so pleasant and so simple is that instead of having billions of fractions, it turns out that there are actually only 7 different fractions. Every element in F7 is one of these 7 numbers. I want to convince you of that. For example, suppose that I wanted to convince you that 3 over 5 is actually one of these 7 numbers. How would I do it? There's a 5 in the denominator. I'm going to take each of the 7 numbers and multiply them each by 5. 1 times 5 is 5, 2 times 5 is 10, which is the same as 3, and so on. And I want you to notice that these 7 numbers that appear here are just a rearrangement of the 7 numbers that we started with. In particular, the number 1 is occurring somewhere as 5 times something. 5 times 3 is 1. That's telling us that the inverse of 5 is 3. So if we want to simplify a fraction like that in F7, we multiply the top and the bottom by 3. 5 times 3 is 15 in F7, which is 1. And 3 times 3 is 9. So this fraction is the same as 9, which is the same as 2. Every fraction in this way can be converted into just an ordinary integer between 0 and 6. And now just a quick demonstration of why it's true that these 7 numbers are a rearrangement of these 7 numbers. I claim that when you multiply by 5, no two of these can be the same. Because if 5 times a equaled 5 times b, it would mean that 5 times a minus b is 0, which means that 7 divides 5 times a minus b. And because 7 is a prime number, if it divides a product, then it must divide either the first or the second element in that product. That's really the main place where we use the fact that we're using a prime number as the base. Well, 7 doesn't divide 5, so it has to divide a minus b. And if it divides a minus b, then a equals b by definition. So different numbers here get mapped to different numbers there. And we really do get a rearrangement of the 7 numbers that we started with. That works for any prime number. So that observation that we just made has an important consequence that goes back to Fermat, a 17th century brilliant French mathematician. And it's the following rule, that if we're working in F7, then any power a to the 6 is equal to 1, as long as the a is not equal to 0. So let's here show why that's true. If you take the numbers 1, 2, 3, 4, 5, and 6 and you multiply them all together, then that's the same as the product of a times 1, a times 2, up to a times 6. Because these 6 numbers are just a rearrangement of these 6 numbers. Last time I showed you the case a equals 5, but it works for any a which is non-zero. Now if you look at this equation, there's a 1 times 2 times 3 up to 6 on the left and on the right hand side. And if we cancel those, we just left with 1 equals a 6 times. So 1 equals a to the 6th in F7. It's a very useful and interesting property of numbers. It's actually a property of number theory. So here, for example, in F7, 2 to the 6, which is usually 64, you can subtract multiple of 7, and you see that it's equal to 1, just like the rule says. If you take 3 to the 6, it's ordinarily 729. You can subtract that multiple of 7, you get 1. You can check that this is true for any power to the 6th. And in fact, it extends not just for F7, but for any prime field. Alright, so now we have to ask, how do we visualize F7? I've told you that there are really only 7 elements in F7. We can think of them as the numbers 0 up to 6. So one way of thinking about F7 is to visualize it as the 7 points on the number line. Actually, it's probably better to identify this point 0 with this point 7, and also with the next ones 14 and 21. That's one way of visualizing it, as numbers on the number line, every 7th one being identified. We can wrap this number line around to form a circle because of that repetitive nature. This way 0, 1, 2, 3, 4, 5, 6, 7 goes back to 0. So 7, 8, 9 is the same as 0, 1, 2. So another way of thinking about F7 is as 7 points on a circle. And you do arithmetic sort of the way you usually do on a number line. Say 6 plus 3 equals 2. There's 6. Go 2 more. No, go 3 more. And you're at 2. 2 minus 5 equals 4. 2 minus 5. 1, 2, 3, 4, 5. You're at 4. And so on. So that's another way of visualizing geometrically what F7 looks like. Alright, when we do geometry, we don't want to just work on the line, we want to work in the plane. So, we consider a pair of coordinates, an F7 in this direction and an F7 in this direction. That'll be 49 points altogether, labeled 0 through 6 and 0 through 6. So the points of F7 are just the intersections in this grid. And we should think of things in a sort of a wraparound fashion. So if we kept on going like this, the next one would be really the same as the one where we started like this. Mathematicians have a way of thinking about this when you wrap a square by identifying or gluing this side to that side and then gluing the bottom to the top. When you glue once, you get a cylinder, and then when you glue again, you get what's called a torus or a donut. So another way of thinking, perhaps a little bit slightly better geometrically, is to think of these 49 points as being distributed on 7 lines this way and 7 lines this way on a torus or a donut. But that's a little bit too hard to visualize, so we'll stick to this planar representation. Alright, we want to do geometry, so we want to talk about quadrants and spread. What is the quadrants between the point A and B? It's exactly the same definition as usual, except that we are always working in F7 now. So we take the difference between the x-coordinates, square it, and add the difference between the y-coordinates, and square it. You get 1 squared plus 2 squared, that's 5. So the 3 quadrants formed by these 3 points are 5, 4, and 6. And lo and behold, it turns out that 5 plus 6 is 11, which is the same as 4. So this triangle is actually a right triangle by Pythagoras. What about spreads? The line through A and B, in the usual fashion, has equation 2x plus y minus 5 equals 0. The line through A and C is 5x minus 3y equals 0. We take 2 times 3 minus 5 times 1, all squared. And on the bottom we take 2 squared plus 1 squared times 5 squared plus 3 squared. So the spread between the lines AB and AC is 1. Also alerting us to the fact that that's actually a right angle or a right spread. So we have the ingredients for doing trigonometry over a finite field. Question is, do all the formulas that we've already established work in this rather strange situation? Next time, I'm going to show you that they do. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.